What's up guys, it's Iman Fiaz and today's video is on AQA AS Level Chemistry June 2020 Paper 1, only Section A walkthrough. Because Section B is multiple choice questions, and for Section B multiple choice questions I'm going to figure out a way for me to go through multiple choice questions. I'm thinking is doing 5 multiple choice questions a day, so then that's 30 times by 5, which is 150 a month, and then 150 times by how many months, like 3 months, so then that's 4 months, so then that's 500, 450 to 600, 450 to 600 multiple choice questions done by just doing a small thing of 5 multiple choice questions a day. That's what I'm thinking, and I probably might do that instead of just going through them all in one go. Then it says a general trend. Give an example of an element that deviates from its trend. So why does it general trend and increase? One element that deviates from trend period 3 is sulfur, because in sulfur the paired electrons repel. So in sulfur the outer electrons, I need to be specific, outer electrons in 3p orbital pair and paired electrons repel. Give an equation for represent the process that occurs. Oh, that's the volume. I want the brightness a bit lower. That occurs when the third ionization of sodium is measured. Classic question again. They always like to ask this question, especially on the AS level papers. Identify element X. So what I would look at here is where's the massive jump in ionization energy? Here, right? And so the outer electron, so how many electrons is it going to have? Well, then I need to look at the periodic table. So data sheet, phosphorus, no, sorry, that's 5, period 3. Yeah, it's going to be phosphorus. Because outer electrons being removed here, 5 to 6, that's a massive jump in ionization energy. So it's got to be the element in group 5. I know it's in period 3, so 1, 2, 3. Here, group 5, so therefore it's got to be phosphorus. That's one way of looking at it. So phosphorus, because, but then the explanation, that's not the reason why it's phosphorus. The explanation is that the idea of large jump in ionization energy after the 5th electron is removed, after the 5th electron is removed, as this is when the electron is being removed from an energy level that is closer to the nucleus. Phosphorus large jump in ionization energy after the 50th electron is removed. This is when the electron is being removed from electron energy when this is when the electron is being removed from an energy level that is closer to the nucleus. Question 2, calculate mass of sodium hydroxide used to make the original solution. Okay, I'm just checking the further questions for question 2. So first thing I would do is find out the title. Why else would it give me this? So I'm going to use that data, concordant titles, divided by 2. And this is going to play a big part in what I'm going to do next. 19.575 centimeters cubed. Perfect. And I know 25 centimeters cubed sample of solution is placed in conic flask and titrated with this much specific acid. I want to find out the moles, the mass of sodium hydroxide. So what I can do now is then find out the moles of sodium hydroxide, and it's not going to be 25 times by this. No, it's not going to be that. That's how much the sample is. Why else would I find out the mean titer here? I'm going to use this. So it's going to be 19.575. No, this is not the moles of sodium hydroxide. It's the moles of H2SO4. Yeah, because it's sulfuric acid, the concentration of so H2SO4. I don't know why I wrote sodium hydroxide. H2SO4, that divided by 1000 times by 0.150. So my answer divided by 1000 times by 0.150. And that's the moles of sulfuric acid. I want the moles of sodium hydroxide. So now I times it by 2 because it's 2 to 1 mole ratio. But then I realized this is 25 centimeters cube sample. That's 200 of that. So I need to then times it by 8. My number of moles. And I get 0.04698 moles. Then I want to find out the mass of sodium hydroxide. The moles is mass of the MR. Mass is the moles, my answer. Times by the MR of sodium hydroxide, 23 plus 16 plus 1. And I get 1.88 grams. Perfect. The student uses a funnel to fill the burette with sulfuric acid before starting titration. After filling, the student forgets to remove the funnel from the top of the burette. Suggests why this might affect the titer volume recorded. The idea that additional drops of solution could have entered the burette from the funnel, hence making the value on the burette lower. Additional drops of solution could have entered the burette from the funnel, hence making the value in the burette lower. State one advantage of using the conic flask rather than beaker: less chance of splashing. That's, yeah, you can say that. Less chance of splashing. That's fine. But with less chance of splashing when swirling. When swirling. Or you could say less chance of losing any solution, but less chance of splashing when swirling is fine. Define the term or relative atomic mass. Classic question again. An average mass of an atom of an element on a scale where an atom of carbon 12 is 12. Average mass of an atom of an element on a scale where an atom of carbon 12 is 12. 2 marks, just memorize the definition, that's all you need to know. Calculate relative atomic mass of this sample of krypton, you give the answer to 1 decimal places. So what you would do is you would do this times by this plus this times by this plus this times by this plus this times by this divided by all of that. Now I'm just going to put that in the calculator instead of writing it all down. So it's going to be 82 times by 6 plus 83 times by 1 plus 84 times by 28 plus 86 times by 8 divided by 6 plus 1 plus 28 plus 8. And there are examples where they, and then times it by, no, and then leave it like that. And I get 84.1. And it's not a percent, it's just AR, so that's fine. 84.1. There are examples where you have to use algebra and then all of that. Those are definitely more complicated, and those are worth up to around about 3 to 4 marks. And those are more common on A-level papers. So yeah, if you want to know how to do it, just practice time. And all of them are very similar. Like they'll give, for example, they'll give you a value and they'll have 2 missing values. You have to let one equal to x, and then the other one is just 100 minus whatever you have already minus x, and then construct the equation and rearrange to find x, and then you find out your ARs or your percentage abundances. Then it says time of flight mass spectrometer, calculate length of flight tube, time of flight tube. So I'm going to use velocity is distance divided by time, and therefore I want to find the length of the flight tube. Therefore distance is velocity times by time. So I'm going to have to find the velocity, I'm going to have to find out the time, but I already know the time. So I have to find out the velocity, and velocity is, alhamdulillah, square root of 2ke divided by m. And the 2ke bit is easy. That's 2 times by kinetic energy given in the question, 4.83 times by 10 to the power minus 16 joules, right? 10 by 10 to the power minus 16 divided by the mass of the 84 Kr plus ion, which is just going to be 84 divided by 6.022 times by 10 to the power 23 times by 1000, or basically 84 divided by that and divided by 1000. So let's work that out. 84 divided by 6.022 times by 10 to the power 23 times by 1000. Then I get that, and the velocity is square root of 2 times by 4.83 times 10 to the power minus 16 divided by my answer, which is, I get the velocity as a ridiculously large number, 83,218.38739. I want the length of the flight tube, the distance, so it's going to be that times by the time, which is that. So it's just going to be my answer times by 1.72 times by 10 to the power minus 5, and then I get 1.43 meters. Perfect. Find out the mass of the ion, rearrange to find out the velocity. Once you've got the velocity, distance and velocity time by time, because you get that from velocity distance divided by time. You've already got the time, and you get your final answer. Say the meaning of the term enthalpy change as applied to a chemical reaction. It's the heat energy change heat energy change at constant pressure. Again, another definition question, and these definition questions are very, very annoying if you don't ultimately memorize the definitions, obviously. So memorize them. Heat energy change at constant pressure. Then it says it should use the data to determine the value for the enthalpy change. There's a method. Explain how the experimental method could be improved. This type of data could be used to determine accurate value for the temperature change. So how can you improve this method, and the use of apparatus? So already I can see one. Measuring this with a measuring cylinder, no. I use a pipette. Pour the acid into a glass beaker, polystyrene cup. And then use powdered solid. So you can already see a couple. So yeah, let's talk about the apparatus. Stage one, the apparatus. So what I'm going to say, apparatus, is we need to use a burette. Use a pipette or burette, doesn't really matter, but pipette instead of a measuring cylinder. Use a polystyrene cup instead of a beaker. And why do we do that? As it insulates the beaker. Reweigh the watch glass after adding the solid. Didn't say that part, so reweigh it after adding the solid. And then the final one, use powdered solid. Maybe the one that's probably maybe not talked about as much, use powdered solid. It doesn't say it's powdered solid. Stage two, well, the temperature measurements, and then the final one, the temperature determination. So temperature measurements. So measure and record the initial temperature of the solution for a few minutes before addition. Measure and record the temperature after the addition at regular intervals until a trend is observed. And then stage 3, temperature determination. Plot a graph of temperature against time. Extrapolate to the point of addition and then determine your temperature change, or determine accurate temperature change at the point of addition, because that's when no heat loss had happened. And these practical questions, you know, in A-level chemistry, then the paper 3 AS, obviously paper 1 and paper 2, the practical questions, same with A-level, could come up on paper 1 and paper 2, but a lot of the time the 6-mark practical questions come up in paper 3, right? And these practicals are just how well have you reviewed them, how many times have you reviewed them. If you've only reviewed it once, let's say this practical, the enthalpy change practical, you're probably not going to get high marks. But if you reviewed it, I don't know, 10, 20, 30 times, you're going to know exactly what to do. You're going to know the mistakes, in this case of the student's method, how to replace the mistake, improvements, and and how to carry out the full method just by heart. And that's what you need to be able to do. Then it says question 4.3, in a different experiment, this much aqueous sodium hydroxide, aqueous hydrochloric acid reacted with this much aqueous sodium hydroxide. Initial temperatures that calculate maximum final temperature of the reaction mixture. Okay, so I want to find out the final temperature of the reaction mixture. I'm obviously going to use delta H as Q divided by number of moles, but I also know Q equals MC delta T, and therefore delta T equals Q divided by MC. But there's no way I can find out Q using Q equals MC delta T, because think about it, actually no, I can, because I've got the mass of the water. Yeah, that's what I was thinking, but no, I can't, because even if I've got because the M stands for mass of water, I'm trying to find out delta T, which I don't know, so I can't use that. So I'm going to keep that like that, but what I can do is rearrange this equation, so I can say Q equals delta H times by moles, and I've got delta H minus 57.1. And now be careful, be very careful with your converting between units. So minus 57.1, and now I'm going to times it by the moles, but the moles of what exactly? Well, this, right? So 50 divided by 1000 times by 0.500. And it doesn't matter whether you do HCl, let me write that down, it doesn't matter number of moles of HCl or number of moles of sodium hydroxide. Why? Because same concentration, same volume, so it's going to be 50, let me put the light on, it's getting a bit dark. $50 divided by 1000 times by 0.500, 0.025 moles. Then I can work out Q, because 0.025 is the number of moles, so it's going to be minus times by 0.025. But this minus sign just tells me it's exothermic, so I don't include it in my calculations. So I get Q equals 1.4275 kilojoules. I don't include the negative sign because that's not going to do anything, because I can have a negative temperature, but I'm not going to have a negative temperature. I want to try for maximum final temperature. So then I'm going to use delta T is Q, which I just worked out, over MC. And what's MC? Well, MC, this is mass of water. And how do I work out the mass of water? Well, in this case, it doesn't give it me, but it says assume 1 gram per centimeter cube, 50 centimeters cube, 50 centimeters cube, so that's 100. So it's going to be 1.4275 divided by 100 times by 4.18. And then that will give me delta T. Yes, but delta T, I want it in degrees Celsius, not Kelvin. So then I'm going to use times by 1,000 then. That's another trick. Yeah, I want it in degrees Celsius, so I need to times it by 1,000. So it's going to be 1.4275 times by 1,000. Then I get the temperature, delta T, as 3.415 degrees. What is that? That's temperature change. And I know the initial temperature was 18.5. And I know temperature increase because it's negative exothermic. So I'm going to do 18.5 plus my answer. And then I get 21.9 degrees. C. Suggest how, without changing the apparatus, experiment question 4.3 could be improved to reduce the percentage of resulting in the temperature change. Now, normally this is about use a larger mass of solid, use a larger mass of fuel, so temperature change is greater of a reducing percentage of 13. But in this case, I'm working with solutions. So you need to really apply it to the question. And what I'm going to increase the solution, I'm going to increase the concentration of solutions. Increase the concentration of the solutions. Increase the concentration of the solutions. 5.1. Experiment with multiple point of magnesium higher than multiple point of sodium. Cool. Not a classic question. Actually, no, it is a classic question. I've definitely seen this before. Magnesium has a greater charge density, and then I would show the examiner Mg2 plus vs Na plus. So stronger ionic, no, it's not ionic. In this case, stronger metallic bonding. Because I remember past paper question, this was on A-level paper 3, aka chemistry paper 3, and it was like, explain why the melting point of magnesium oxide is higher than the melting point of sodium oxide. In that case, you would say magnesium has a greater charge density, Mg2 plus Na plus, but then you wouldn't say, then you would say stronger ionic bonding because it's between Mg2 plus and O2 minus because it's oxide. But in this case, it's just magnesium, so it's metal. So stronger metallic bonding, stronger attraction between delocalized electrons, stronger attraction to delocalized C of electrons. Given equation, show how magnesium is used as a reducing agent in the extraction of titanium. I know I'm going to form Ti solid plus 2 MgCl2 gaseous. It doesn't even ask me for state symbol, so I'll just cross it out then. Why risk getting them wrong? So state symbols are wrong. So it's TiCl4 plus 2Mg. That's what it is. 2Mg plus TiCl4 to form Ti plus 2MgCl2. So in terms of oxidation state, where magnesium is the reducing agent. So I have to talk about the oxidation states, and I would say magnesium changes oxidation state from, in this case, 0 on the left hand side, the reactants, to, don't care about the moles, chlorine is -1, -2 to +2. So electrons are lost. And it's only going to be a 1 mark explanation. Or I could say titanium changed oxidation state from +4 to 0. It doesn't really matter. But yeah, just talk about the oxidation states and how they change. And you should get the mark. TiCl 2Mg plus TiCl4 to form Ti plus 2MgCl2. Magnesium change oxidation from 0 to +2, so electrons are lost, and that part is really important. Question 5.3 state was observed when dilute aqueous sodium hydroxide added to separate solution magnesium chloride and barium chloride. Dilute aqueous sodium hydroxide added to separate solution magnesium chloride and barium chloride. Slight white precipitate. And remember, with the barium chloride, you've got the Ba2 plus, and remember that's no visible change. No visible change. Slight white precipitate, no visible change. Question 6, George shapes NCl3 and NCl4 plus. So NCl3. And these like wedges and these dashes coming out just shows that the thingy that the shape is 3D. NCl4 plus again, and but in this case I've got chlorine here, got chlorine here, got wedge over here, and I've got chlorine here. Name of shape of NCl3. I've got 3 bonding pairs, 1 lone pair, so it's going to be trigonal pyramidal. Or yeah, trigonal pyramidal. But in reality, I guess, yeah, pyramidal. Just need pyramidal. NCl4 plus, that's going to be tetrahedral. But no, we want a bond angle, sorry. So 109.5 degrees. And the thing about NCl4 plus is you can't talk about lone pairs of electrons for your explanation to explain bond angle, because it's got 0 lone pairs. It's got 4 bonding pairs, 0 lone pairs. It's tetrahedral. So you need to talk about just the electron pairs. So electron pairs repel equally. Electron pairs repel to be as far apart as possible. Electron pairs repel equally. Electron pairs repel to be as far apart as possible. Chlorine is used to treat water even though it's toxic to humans. Give one reason why water is treated with chlorine. Reason kills microorganisms. Wait, what? Explain why chlorine is added to water even though it is toxic. So one reason why water is treated with chlorine, yeah, because it kills microorganisms. Kills microorganisms. Explain why it's added even though it is toxic. Only used in small quantities / low concentrations. Used in small quantities / low concentrations. Kills microorganisms. It's only used in small quantities / low concentration. And the equation, I knew there was going to be an equation question eventually. HCl plus HClO. There you go. How well have you memorized your equations? That's all it's testing this part. This one, it kills microorganisms. This expansion, a bit of application because it's only used small quantities / low concentrations. Half equation conversion of this, and then okay, a lot of equations. So solid sodium iodide reacts with concentrated sulfuric acid to form iodine and sulfur in a redox reaction. Give a half equation to show the conversion of iodide, so I minus, to iodine. So I need a 2 here, and then 2 negatively charged electrons here. sulfuric acid, H2SO4 to sulfur. So first thing I would look at is H2SO4 to sulfur. First thing I would look at is, okay, I need to add 4 oxygens, right? So 4 H2O. But now I've got 8 H plus on the right side and I've only got 2, so then I need to add 6 H pluses here. But then I also need to add 6 E minuses here. Are the charges balanced? Yes, is everything yes, is everything else balanced? 2 hydrogens, no sorry, 8 hydrogens, 8 hydrogens, 4 oxygen, 4 oxygens, sulfur, sulfur. Perfect. Then overall equation, I've got 2 here, I've got 6 here, so I need to times this first equation by 3, and I get 6I minus arrow 3I2 plus 6E minus, negatively charged electrons cancel out. Then I'm left with 6I minus plus 6H plus H2SO4 to form 3I2 plus sulfur plus 4H2O. And I think it was the last past paper I did, went through, walked through, maybe the one before that, and it was like, yes, that's your final answer, but in reality it wasn't, because there's H pluses on both sides. So then remember to make that further step, or there's H2Os on both sides, so cancelling them out. But in this case, everything's perfectly fine. So 2I minus RI plus 2 minus 6E minus plus 6H plus H2S4 from sulfur plus 4H2O, 6H plus 6I minus plus H2S4 from 3I2 plus sulfur plus 4H2O. And then it says other sulfur containing reduction product. Well, it could be, you could say sulfur dioxide or hydrogen sulfide, probably what I would say hydrogen sulfide, but any of those two are fine. Silver nitrate added solution suggests when excess is used. To ensure all the halide ions are removed from the solution, or to ensure all the halide ions precipitate out of the solution. Calculate amount of moles of silver iodide obtained. Well, it's just going to be the moles mass of ml, but I've got the mass in milligrams to grams, so I need to divide by 1,000. So all it's going to be is 0.315 divided by 234.8, and that's why it's 1 mark. But there is one step, obviously, of convert from milligrams to grams. But once you've done that, then you can get your final answer. 1.34 times by 10 to the power minus 3. To ensure all the halides are removed from the solution, ensure all the halides precipitate out of the solution. Question 7.5. You calculate using the answer to question 7.4 the mass in grams of sodium iodide in the mixture. Well then, the mass, well, moles is mass of mR. Mass is going to be the moles, which I just worked out, times by the mR of sodium iodide, 149.9, 0.201 grams. Then it says, calculate using answer to question 7.5 the percentage by mass of sodium chloride in the mixture. Well, sodium chloride, complete experiment to determine the percentage by mass of sodium chloride in mixture sodium chloride and sodium iodide. 600 milligrams of this. Mass of silver iodide, sodium iodide, sorry. So now I've got sodium iodide. I know the total mass of the mixture is that. So I'm going to do 0.600 minus 0.201, or minus the answer of my calculator, 0.399 divided by 0.600, because that's the mass of sodium chloride times by 100. So then my answer divided by 0.600 times by 100, and I get 66.5%. So Number of moles 1.34 times by 10 to the power minus 3. The mass 0.201 grams. And then the mass of sodium chloride. You just need to read the question properly, and then you can see, okay, so all I've got is sodium chloride, sodium iodide. I've got the mass of sodium iodide. I know the total mass is that. So if I do that minus that, I'll get the mass of that. And then the percentage by mass is that. It's just going to be that mass over the total mass. And then that's what you do. And in reality, I didn't even need to convert it into grams because it would have been the same if it was milligrams or not. Because 399 divided by 600 is the same as 0.399 divided by 600 times by 100. But it's fine. And then question 8.1. Calculate the MR of A. Give you answer to 3 single figures. The gas constant R is that. So first thing I know I'm going to need to do, I think PV equals nRT. Ideal gas equation. But also to give me the volume, pressure, and the temperature. MR, so I need to work out the moles. PV divided by RT. And then I'm thinking, okay. The pressure is, wait, what? Yeah, because I've got the mass. I know the mass is just difference between these two. And then once I've got the mass and I've got the moles, then I can work at the MR. That's what I'm going to use. So pressure in pascals, 100 kilopascals or 100,000 pascals, times by the volume in meters cubed, and that's in centimeters cubed, and centimeters cubed in meters cubed, so I need to divide by a million. 178 I'll put times by 10 to the power minus 6 divided by R, which is 8.31, times by the temperature in Kelvin, 120 degrees Celsius. I don't care about that. I want it in Kelvin. So 120 plus 273, 393. Now, before I even do that, let me work out the mass of A. The mass of A. And it's just going to be mass of fine needle, syringe, and contents before injected minus mass of fine needle, syringe, and contents after injecting. So 11.295 minus 10.835. 0.46 grams. Then I work out the number of moles. I just put all of the values in my calculator with the correct units. 1, 2, 3 times by 178 times by 10 to the power minus 6 divided by 8.31 times by 393, and that's the number of moles. And I know moles is mass over MR, and I want to find the MR. Therefore, MR is mass divided by number of moles. And I just want to double check something. Yeah, I was just like, if it's done by electron spray ionization, then you minus 1 for the MR. There are a couple of tricks with those kind. I've seen them before. But yeah, in this case, it's not that. So it's just going to be 0.46 divided by number of moles, and I get the MR as 84.39785,393. So I guess 84.40 should be fine. But it said give you answers to three significant figures. And I keep missing that out. I keep not reading that. So therefore the answer is 84.4. So N equals B divided by RT, find the number of moles. Then MR is mass over mole, and you get that. And remember to three significant figures. For 4 marks, not bad. Just need to know your correct units and rearrange it pretty well. And all you're doing is PV divided by RT. That's it. And then obviously mole mass of MR. Then it says, student noticed that some of the liquid injected into the gas syringe did not vaporize. Explain the effect that this has on the MR calculated by students. So lower volume recorded. Oh, no, actually, first thing I would say, calculated value of calculated MR value would be greater than the actual, because the student noticed that some of it did not vaporize, so the calculated MR value would be greater than the actual, as the lower volume would have been recorded. because if you think about it, right, you need to think a bit more deeply for this one. But the idea is, you notice some of the liquid did not vaporize. So if it didn't vaporize, well, then what's going to happen to the volume? Well, the lower volume would have been recorded, and what would happen to the MR? Well, if lower volume is recorded, N equals PV divided by RT, so the number of moles would be smaller, and if the number of moles is smaller, then the MR, the actual MR would be smaller. No, the calculated MR value, yeah, the calculated MR value would be greater than the actual. The actual MR value would be smaller. So calculated MR value would be greater than the actual, as lower volume has been recorded. Each reading on the balance used to record the mass of fine needle syringe and contents of uncertain. This calculated percentage of certain mass of liquid air injected in the experiment. So it's going to be 0.001 divided by mass of liquid A, which is 0.46, times by 100, but mass of fine needle syringe and the contents only times by 2, because I'm doing one mass subtracting another mass, and that's really the tricky part for this question, spotting that. 0.43%, that's fine. Or 0.435%. And that's the end of section A.